Find the radius of curvature of the following curve at the given point. Now, the radius of curvature at a point P is defined as 1 by kappa, where kappa is the curvature at this point. Now, here we are given the beautiful vector-valued function r of t is defined by the vector with components t, 2t squared. And now the point P that we're considering is t equals 0. So we have two options for curvature here. I'm going to use that second form of our definition. So let's just quickly recall that the curvature, kappa, using that alternative definition or that second formula, is defined as the magnitude of the cross product of the tangent vector with the second derivative. So you can also think about this as the magnitude or the length of the cross product of the velocity vector with the acceleration vector. And then we divide this by the magnitude of your tangent vector cubed. So this is the formula that we're going to use here to compute the curvature for this parameterized curve. And then we'll use that curvature to find the radius of curvature. So here we go. Starting with our beautiful parameterized curve, parameterized by this vector-valued function, I'm going to begin by finding the tangent vector, the velocity vector. So differentiating here, we are left with the vector with components 1, 4t, beautiful. And let's go ahead and find the second derivative, or the acceleration vector. So our second derivative leaves us with 0, 4. Fantastic! So we also want to keep in mind here that we are concerned with the curvature when t is 0. So let's take a moment and evaluate these. So our tangent vector when t is 0 leaves us with 1, 4 times 0. So we are left with the vector with components 1, 0, a cute little unit vector there. And look at this, when we evaluate the second derivative or the acceleration vector at 0, we're still left with the vector with components 0, 4. And we could, if we want, pull out a scalar multiple of 4. So that's 4 times the vector with components 0, 1. Beautiful. So using these, let's go ahead now and find the cross product of these two vectors. Now keep in mind that the cross product is defined in R3. So we have two vectors here in R2. So in order to compute this cross product, we need to add the z component, which will be 0. So here we go. We have the cross product of these two vectors, the velocity vector and the acceleration vector at t is 0. So putting them right into that 3 by 3 determinant, I have a row of unit vectors, I hat, j hat, k hat. The tangent vector has the components 1, 0, 0. And the acceleration vector has the components 0, 1, 0. And don't forget, I factored the scalar multiple of 4 out, so we want to keep that scalar multiple 4 on the outside of the cross product. So this is going to leave us with 4 multiplied by 0 minus 0 I hat minus 0 minus 0 j hat plus 1 times 1 is 1 minus 0 k hat. So we're left here with just 4 k hat. Or we can rewrite this in its component form. So the cross product here of these two beautiful vectors is the scalar multiple 4 times the vector with components 0, 0, 1. Beautiful. So we now want to go ahead and take our tangent vector, evaluated at t is equal to 0, as well as this cross product, and find the length of these two vectors. So thinking about, we'll do the cross product first. The length of the cross product of the velocity vector at t is equal to 0 with the acceleration vector at t is equal to 0 is going to be 4 times the distance formula, the square root of 0 squared plus 0 squared plus 1 squared, which of course leaves us with 4 times the square root of 1, which is just 4. And we already know what the length of our tangent vector at t is equal to 0 is going to be, because it's a unit vector. So we have everything that we need, and we're ready now to find the curvature at t is equal to 0. And giving ourselves plenty of room, we can say our curvature, kappa, at t is equal to 0. So we have, again, kappa is defined as the magnitude of the velocity vector at t is equal to 0, crossed with the acceleration vector at t is equal to 0. And we are, again, dividing this by the magnitude of the tangent vector at t is equal to 0 cubed. So we have 4 by 1 cubed, which is 4. Now, be careful. We don't want to get so excited that we found curvature that we forget our whole goal here is to find the radius of curvature. So the radius of curvature for this curve at t is equal to 0 is defined as 1 by kappa, our curvature. So that's going to leave us with a beautiful final answer of 1/4. And so there you have it. The radius of curvature is 1/4.